Sounds good. Yeah, so I'm going to be talking about cutting planes proofs of random formulas and Tseitin formulas. So this is based on joint work with Patasi, Pankratov, and Robert, and also on recent new work by Deduch and Tuari that I find really exciting. Yeah, so it's going to be in the field of proof complexity, so I'll give you a little overview of what that is. This is propositional proof complexity. So in proof complexity, we're interested in the question of how hard is it to prove a propositional tautology. Okay. So let's be a bit more formal with this. So by a propositional tautology, we're just going to mean a tautological DNF. And often it'll be convenient to switch between proving a tautology and refuting its negation, which is a unsatisfiable CNF formula. So I'm going to switch back and forth between these. So we need to formalize what we mean by prove. And this is going to be in some proof system. So a proof system is just a set of lines and a set of deduction rules. You don't really need the set of lines, but I think it's a nice way to think of it. So the deduction rules allow you to take previously derived lines and derive a new line. And we want some conditions on what sort of things we can derive. So we want our deduction rules to be sound. So this just means that you can't prove anything false with them. Complete, which means that you should have a proof of every propositional tautology, and our computational assumption, which is that they're efficiently verifiable. Which just means that you can check the deductions in polynomial time. Okay, so a standard example of a propositional proof system. So it's resolution. And this is an example of a refutational proof system. So you refute the negation of a tautological DNF. So you refute a CNF formula. And so the lines in resolution are clauses. And you have one rule called the resolution rule. So you're allowed to take two clauses, A or X, and B or X bar. So two clauses with complementary literals in them, and derive a new clause, which is the disjunction of the two previous ones with the complementary literal removed. And the goal in resolution is to derive the empty clause, which is just like a trivial certificate that you have refuted the unsatisfiable CNF that you started with. Okay, so why care about proof system, about proof complexity? So the main reason, which was Cook's original motivation for studying proof complexity, is the P versus NP problem, or NP versus co-NP problem, sorry. So we can show that there's a proof system with short proofs of every tautology. If and only if NP is equal to co-NP. And this is pretty easy to see. Basically, a proof system is just an NP machine for the co-NP complete language of tautologies. Okay, so if we want to prove that NP is not equal to co-NP, we need to come up with a candidate family of formulas which we think might be hard for every proof system. So said differently, if you want to prove that NP is not equal to co-NP, you need to show that there's some family of formulas which doesn't have short proofs in any proof system. So what candidate of formulas can we have? Candidate formulas. So our standard candidate, well, one of them right now is random CNF formulas. And this is going to be one of the two tautologies that I talk about during this talk. So what's a random CNF formula? And I'll get to why we think that these are hard. So we generate a random CNF from the distribution FMNK by picking M clauses uniformly at random from the set of all K clauses. Okay. Yeah, so I said that we think that these are really hard to refute. Oh yeah, so one thing to mention, these are CNF formulas, and therefore we're going to be talking about refuting them. So I mentioned that we think that these are really hard to refute, but of course, we need to specify for what range of parameters, because if you say, for example, you made M very large in terms of N, like M is like 2 to the N or something like that, then you're going to get almost every clause and they're going to be really easy to refute. On the other hand, if you have very few clauses, like M some constant, then these formulas are going to be satisfiable with high probability. So first of all, we need to guarantee that these random CNF formulas are unsatisfiable. So it's well known that there's a threshold some C sub k, such that if the clause variable ratio, M over N, is greater than C sub k, then the random CNF formula you pick is going to be unsatisfiable with high probability. And this threshold turns out to be tight or sharp. And if you pick a random CNF formula near this threshold, near C sub k, then empirically, it's been, empirically we have a lot of evidence that random CNF formulas are going to be extremely difficult to refute near this threshold. And we also have a lot of theoretical evidence showing that these are hard for certain proof systems. Yeah.
I'll make a comment. Maybe for people who haven't seen it or haven't seen it for a long time, it may seem bizarre that you are allowed to take random objects as a source of lower bound. So the point here is that unlike in circuit complexity, where we know that random functions are hard, it's not interesting to us. In proof complexity is a very different situation, and proving lower bounds for random tautologies or contradictions is good enough. So it will, can prove potentially NP different than co-NP.
Yeah, exactly. And no counting argument goes through like in the circuit world.
Can I ask you something also?
Yeah.
Can you say what is K again?
Yeah, so K is the width of the CNF formula. So the number of variables in each clause.
Okay. There was a dash missing. Okay, now I understand.
Actually, no, and to follow up to Avi's comment, you might want to mention the point that you were making to me a little while back about why, in some sense, it's necessary to look at.
Yeah, I wasn't sure if I wanted to get into this, but
just make a comment because I think it's interesting.
Yeah, so one of the things you have to, one of the things you can observe is that, in fact, these, if you want to have some candidate hard family of formulas, then this family has to be very dense, meaning that for every n, there has to be a lot of instances of that family of formulas.
So what he means though is hard for any proof system.
Yeah, exactly. And the reason is if these family of formulas is sparse, say there's one instance for every n, then you can always define a new proof system which has this family of formulas as an axiom. So said differently, here's a proof system for this candidate family of formulas. So let's say this family of formulas, phi.
Yeah, I don't know if you have to get into all the details, but I just think the high level point of
Basically the point is that these family of formulas has to be dense, because otherwise you can basically define a new proof system by adding this family of formulas as an axiom to your previous proof system. And then in this new proof system that you just defined, this family of formulas is going to have short proofs. So this is a motivation for random formulas because they're extremely dense. So another motivation for random formulas is you can think of it as sort of a non-deterministic version of Feige's hypothesis.
May I ask a question?
Yep.
Yeah, how can you add them if they are non-uniform?
Sorry?
How can you add these witnesses for the specific supposed hard instances, even if they are sparse, if they are non-uniform?
So I don't want to get too into it, but basically what you could define, so proof system's just an NP algorithm, and what the algorithm could do is so it's given as input a tautology, and it could just calculate the length of this tautology, and then calculate then if your family of formulas phi of hard formulas is maybe polytime constructible, and there's few of them, then you could just generate all these instances for n.
Oh, of course, if they are polytime constructible, but they are, but if it's non-uniform, I don't think you can do it. But okay, never mind.
yeah, I think you're both making different points. But I think Noah's just saying that you can't just fix one nice uniform family of, the natural thing would do to take something that we think any proof of it requires, super polynomial circuit type of reasoning. That would be like the natural thing people have been doing so far, and that kind of thing won't work.
Okay.
Yeah.
Thank you.
Yes,
Well, what's the size of the family for every n that you need, according to this argument?
Size? I would think it would be super polynomial, but I'm not totally sure. Yeah, okay, so these are all good questions. So the loose conjecture is that random formulas are hard for any proof system. So for m over n, I'm going to state it very informally. For m over n near the threshold, c sub k. And we also want k to be greater than or equal to 3 because 2 sat's easy. Then with high probability, random CNF formula is hard for any proof system. Okay, so there's been progress on resolving this conjecture. So I'm just going to review that a little bit because it'll tie in nicely with what I want to talk about next. So the first result was by Vital and Semberetti in '88, who showed that random formulas are hard for resolution. And so this result leveraged some earlier tools by Urquhart, who proved lower bounds on the Tseitin formulas. Okay, and so in fact, almost every lower bound on random CNF formulas for some proof system that we have has followed by lower bounds, has followed lower bounds on Tseitin formulas for that proof system. So what are these Tseitin formulas? So we're given a graph and a labeling of the vertices of that graph. We have, for each edge, we have a variable. And for each vertex, we're going to have a constraint, which is going to say that the mod to sum of the incident edges to that vertex is equal to the labeling. Okay, so an easier way to think about this graphical representation is going to be useful later, but an easier way to think of these Tseitin formulas is as any unsatisfiable system of linear equations mod 2, where every variable occurs in exactly 2 constraints. Oh, and I should mention that these are unsatisfiable if and only if the labeling is odd. Okay, so as I mentioned, all lower bounds on, well, almost all lower bounds on random formulas followed lower bounds on Tseitin formulas. So examples of this are sum of squares, null-Stulin sats, polynomial calculus, and also, well, AC0 Frege if we obtain lower bounds on random formulas. So there's one exception to this trend, which is cutting planes.
No?
Yep.
Yeah, maybe you just want to say that if you want to encode this as a CNF, you want the degree of the graph to be a constant because you have to replace the exclusive OR with conjunction.
Yeah, exactly. So you can encode the Tseitin formulas as a CNF formula, where each mod 2 equation becomes, say, each mod 2 equation has d variables. Then you get 2 to the d minus 1 constraints, one for each falsifying assignment to the equation. So this becomes, let's say m is the number of vertices, and d is the degree of the graph. Then this is m times 2 to the d minus 1 size. So, yeah. All right. So yeah, so there's one exception to this pattern, which is cutting planes. So lower bounds on random formulas for cutting planes were known before anything was known about the complexity of the Tseitin formulas for cutting planes. Okay, so what is cutting planes? So this will be the main focus of the talk. So cutting planes operates over linear inequalities, and therefore we need a way in order to translate CNF formulas into linear inequalities, which preserve the semantics of the linear inequalities. So what I'm going to do is I'm going to take a CNF formula and turn it into a set of linear inequalities which preserve 0-1 solutions. So I'll just do it with an example. Should be pretty self-explanatory. Okay, so here's the CNF formula. And we get the following set of linear inequalities. So, sorry, that should be 4. So each clause becomes a sum. So we get x1, and we replace positive literals with just themselves and negative literals with 1 minus that literal. And we set that all greater than or equal to 1. And same for this guy. And we also want to restrict ourselves to the Boolean cube. So we're going to add in the axioms which say that xi is greater than or equal to 0 and xi is less than or equal to 1 for all I. Yeah, so it's easy to check that this system of linear inequalities has exactly the same 0-1 solutions as the original CNF formula. Okay, so cutting planes, it operates over linear inequalities. Lines. And so we can view every step of the cutting planes proof as a polytope, which is formed by the linear inequalities that we've derived so far, together with the inequalities defining the original CNF formula. And so what cutting planes is going to do is it's going to refute the CNF formula by proving that this polytope has no 0-1 solutions. The way it's going to do this is it's going to apply a set of deduction rules which remove fractional solutions from this polytope while preserving any integer solutions. Yeah, so the goal is to derive 0 greater than or equal to 1. And the rules, first rule, we have addition. So we're allowed to take any number of previously derived inequalities. In practice, I think n+1 is always enough by Carthodori's theorem. And so we're allowed to derive a non-negative linear combination of them. Oop. So alpha I is greater than or equal to 0. And this corresponds to deriving any half space which is valid for this polytope. Maybe I'll try one here. But it doesn't rule out any feasible solutions to this polytope, any fractional solutions. So we want a second rule which can remove fractional solutions from this polytope and make progress on refuting it. And that is the division rule. So what the division rule allows you to do is if you have a linear inequality where all of the coefficients of the variable terms have some factor of a in them, or alpha in them, sorry, you're allowed to divide everything by alpha and round up the right-hand side. Okay, so what this corresponds to doing is sliding in this half space. Let's say it's this green half space here, and we're allowed to slide it into the nearest integer point in the queue here. So this removes all the fractional solutions, and we're left with this polytope. Okay, and the refutation ends when we've derived the empty polytope, or 0 greater or equal to 1. And you can view cutting planes proofs as a DAG in basically the standard way. The leaves are just going to be the axioms, and there's an edge from two lines to the new line if we used derivation rules based on those two children to derive the parent. Okay, so the first formula that was conjectured to be hard for cutting planes were the Tseitin formulas. And this was in the original paper by Cook and others, who introduced the cutting planes proof system. However, when lower bounds on random formulas were proven, there was nothing known about the complexity of the Tseitin formulas.
Just a quick minor thing. So it's really like was introduced in the context of, linear programming optimization by Gomery and Quatal, and then Cook, Clayard, and Turan studied it as a proof system.
Yeah. So as Tony has said, cutting planes started off in mixed integer programming, and it was Cook and all that started to study it in the language of propositional proof complexity.
I think it's a much more general comment, Tony's comment. I think that almost all propositional proof systems capture some kind of algorithmic heuristics or algorithmic ideas used in a variety of search problems. And in some cases, they are logical, like in the case of resolution. In some cases, they are geometric, like in cutting planes and sum of squares and this. And sometimes they are algebraic, like polynomial calculus. And so they are really natural, and they come very naturally in optimization. And propositional proof complexity, another way to think of its motivation is, even without NP versus co-NP, is just to show that various algorithmic techniques used to solve search and optimization problems are just not going to work in some cases.
Yeah, exactly. That's a really nice point. Yeah, and this has been really taking off recently with connections to like SAT solving, and I guess the sum of squares work as well. Yeah, okay, so cutting planes Tseitin was conjectured to be hard for cutting planes. So then nothing was known about Tseitin when we proved lower bounds on the random formulas. So this was in joint work with Potassi, Pankratov, and Robert, and proved independently by Hrubesch and Pudlock. So we proved that for theta log n with random CNF formulas, cutting planes must have exponential size refutations. So one really interesting thing about this proof technique was that it provably would not work for Tseitin. So this proof technique actually worked for a stronger proof system, which has short proofs of Tseitin. So this, to me at least, made Tseitin a lot more interesting of a problem, because it kind of meant that if we're going to prove cutting planes lower bounds on Tseitin, then our lower bound technique has to be very precise to the actual rules of cutting planes. Instead of this technique that we use here that works for a lot stronger, a much stronger semantic proof system. However, in a really surprising recent result, Dadouche and Touare showed that actually the Tseitin formulas are easy for cutting planes, at least quasi-polynomially. Okay, so in a follow-up work that we just submitted, so this is with Goose, Patassi, Robert, Tan, and Impagliazzo. We extend this result to show that cutting planes can refute, quasi-polynomially refute any unsatisfiable system of linear equations over a finite field. So I think these two results are really interesting because basically what they're showing, so you can think of cutting planes as the reasoning that we can capture with linear inequalities over the reals. And what this is showing is that reasoning with linear inequalities over the reals can at least quasi-polynomially simulate reasoning using linear equalities over finite fields. Okay, so these two theorems here are what I want to talk about for the rest of the talk. So I'm going to start with the second one.
Just a question. So can you simulate, let's say, res-lin?
No, I don't think you should be able to simulate res-lin. For this second result, you really need that they're unsatisfiable over the same finite field.
Res-lin over which field?
Sorry? Sorry, I missed that. So maybe. So this is just any finite field here.
Yeah, okay.
And I'll tell you a bit about how to prove this result. I'll prove the Tseitin result because that one's a bit simpler, but the same sort of intuition works for the finite field result. Okay, so I'll start with the Tseitin result because I think it's newer and kind of more exciting.
Just to make sure that I understand the last result.
Mm-hmm.
When you say equations, you mean you have both
So I mean I have a system of linear equations over some finite field that are unsatisfiable over that finite field. And then cutting planes has quasi-polynomial size refutations of them.
Right, but if it's inequalities, every cutting planes instant proof language that is proved by cutting planes is always linear. Here you mean that you have both the factorization.
Sorry, I think you're breaking up a little bit. So one thing you have to be careful with this result is that it does depend on the fact that in order to encode these linear equations into linear inequalities, this induces like a q to the d minus 1 blow up in the number of clauses. So what I mean is that like a linear equation over fq with d minus 1 variables is going to need something like q to the d minus 1 clauses approximately, or linear equations in order to encode it.
Okay, can you hear me? Sorry.
I can now, yeah.
So I don't understand why you need to encode anything, or maybe I missed the encoding.
So cutting planes
Because
can't
it's
read about finite fields, so you need something
because it's
to encode the
finite fields.
field.
Oh, yes.
Yeah,
Sorry.
yeah.
Yeah, and this last theorem is quasi-polynomial.
Yeah, sorry.
Oh, I see. Yeah, thank you.
Was I polynomially? Okay, so the outline of the Tseitin upper bound proof is pretty straightforward, actually. So the first thing to do is we'll prove that a stronger proof system called stabbing planes has quasi-polynomial size proofs of Tseitin. And second, we'll show how to translate this proof into cutting planes. And the second point, I think it's really surprising that it can be done. Okay, so what is stabbing planes? So stabbing planes was introduced in a paper in 2018. The point of it was kind of to make a proof system. So SAT solving had been trying to build proof system, or sorry, the satisfiability solving community had been trying to build SAT solvers, so algorithms for SAT, off of this cutting planes proof system. And we introduced stabbing planes proof system as basically a query analog of the cutting planes proof system to kind of better resemble what was being used at that time in the SAT solving community. So stabbing planes is going to look a bit like a decision tree or a DPLL algorithm where you query linear inequalities rather than variables. Okay, so it works over linear inequalities again. So the input is an unsatisfiable system of linear inequalities, or a CNF encoded as one. Therefore, we can view it as a polytope as usual. And we have one rule. So we're allowed to take an arbitrary integer linear inequality. So for a and to the n, z. And we're allowed to branch on whether this linear inequality is true or false over Boolean solutions. So what I mean by this is we're allowed to say recurse on whether ax is greater or equal to b, or ax is less than or equal to b minus 1. So we either recurse on this half or on this half. And what this looks like is the proof is a binary tree where each node is labeled with a polytope. So call this F and PF to be the polytope associated with it. So the root is just the full polytope. Each node at each leaf, or sorry, each node you branch on an arbitrary integer linear inequality. So, and the children of it are labeled with the polytopes, with the current polytope intersected with this new inequality. So I'm going to use this thing to actually denote x such that ax is greater than or equal to b. Yeah, so on both leaves you recurse on the polytopes intersected with the with this new linear inequality, and you can observe that this slab of points here has been removed. It doesn't survive down either of the two paths down this tree. And this is fine because no integer point is contained within this slab. So, and it's easy to see that any integer point would survive down at least one of these paths. Okay, so we keep branching until we reach the empty polytope, at which point we stop querying along that branch, and the proof is finished when we've labeled each of the leaves with the empty polytope. Yeah, so it's basically just a decision tree where we query linear inequalities rather than variables, and we halt a branch when the corresponding polytope at that node is the empty polytope. Okay, and then the size of a stabbing plane's proof is just the number of nodes in the tree. Okay, is that clear?
Maybe you want to say something about why it's polytime checkable?
Yeah, okay. So it's easy to see that if you have if one of these nodes is the empty polytope, then you can always certify this using Farca's lemma. So by Farca's lemma, there's a non-negative linear combination of the inequalities labeling the root to leaf path together with the original inequalities, which gives 0 greater than or equal to 1. And so you can label the leaves with this certificate of this fact. And this allows you to polytime check whether you've actually reached, to verify that you've actually reached the empty polytope. Okay, so the first part is to show that we have short proofs of Tseitin in stabbing planes. So this was done in joint work with Beam, Impaliazzo, Kolokolova, Patasi, Pankratov, and Robert in 18. Longest
quick question.
Yeah.
Do we know of examples that separate site? Oh, well, so first of all, is it easy to show that stabbing planes can do cutting planes just by kind of a one-to-one replacement? And are there separating examples?
There's no separating examples, but it's quite easy to show that stabbing planes can simulate cutting planes. So I'll get to that in a little bit. Okay, so let's recall what the Tseitin formulas are. There we go. So we have a graph. where each edge corresponds to a variable and each each vertex is a constraint. So I'm going to make a simplifying assumption. This isn't actually that simplifying, but it'll be slightly nicer to think of that LV is 1 for all. So every vertex is labeled with 1, and the size of V is odd, and this means that it's unsatisfiable. So an example of Tseitin graph, which we'll kind of use as a running example, is just the complete graph. So I'm not going to draw the edges here, but yeah, assume that there's an edge between each vertex. And so the upper bound idea is it's kind of a divide and conquer approach. So what we're going to do is first, we're going to partition the set of edges into 2 halves.
Are you drawing something?
Yeah, is it not showing up?
Yeah, it's not showing up anymore.
Oh, there we go. Seems to be lagging for some reason. Well. So we partitioned edges into 2 halves. So maybe this, or sorry, we partitioned the vertices into 2 halves. And then we're going to look at the edges that cross this cut. And we're going to determine the value of the sum of the edges crossing this cut. And once we know this, the sum of these edges crossing this cut, then the parity is going to tell us that one of these 2 halves of vertices is unsatisfiable under this assignment to the cut edges. And you can kind of see this. It's basically by handshaking. So let's suppose that we determined that the sum of the edges were 5, so odd. And that will mean that the set of vertices which have an even total labeling, so that's the red side, is going to be unsatisfiable. And you can see that because if there's an odd number crossing here, and each of these guys need to be assigned a value of 1. So L4 requires 1, L5 requires 1. Then there's no way to internally set this, knowing that all the outgoing edges are odd in parity, just by handshaking in order to satisfy it. And then we just recurse on the half that is falsified. Or unsatisfiable. Okay, so again, we partition the vertices into 2 halves. We figure out the sum of the edges crossing between the 2 halves, and then we recurse on the half that where the parity of the sum of the edges does not match the parity of the labeling in that half. Okay, so we have to figure out how we're going to do this step 2, how we're going to determine the sum of the edges, and we can do this just by branching using the stabbing planes rule on whether the sum of the edges is 0, whether the sum of the edges is 1, 2, so on and so forth. So I'll show you here. So let's let L be the sum of the edges crossing. So x1, 4, x1, 5, x all the way up to x3, 4, x3, 5. And then we're going to ask in stabbing planes whether this is greater than or equal to 1 or less than or equal to 0. Then whether it's greater than or equal to 2, less than or equal to 1, and so on and so forth, all the way down to the maximum value, which is 6. And then observe that each of the leaves of this little tree here, we know that the sum of the edges crossing this cut is exactly some value. For these guys here at the extremes, we're just using the axioms that say that each vertex has value at most 1, or I mean, each variable has value at most 1, and each variable has value at least 0. These are just axioms that are included with our translation to a set of linear inequalities. Okay, so let's look at one of the leaves of this little tree here. And what we do here is we recurse on the side that is unsatisfiable, that doesn't match the parity. So that means that we're going to recurse on the red side here. I'm going to erase these guys. And we're recursing on this thing. So we know that this charge is 1. And we recurse on red. And again, what we're going to do is we're going to partition the set of vertices into 2 halves. Now there's just 2 vertices. And we're going to query the sum of the edges leaving each of these sets of vertices. So query edges. So I'll denote, I'll just denote them by their color: green, without, or keys, yellow, without, yellow, cut, and then at each leaf of this tree, we're going to query the edges crossing the green and be without green cut. Okay. So just do that here. So let's let L be equal to, the x1, 5, x2, 5, x3, 5, x4, 5. And similarly for L, yellow, we're going to let that be x1, 4, all the way up to x4, 5. All right, so again, we query whether this is greater than or equal to 1, less than or equal to 0. Greater than or equal to 2. And all the way up to greater than or equal to 4. And at each leaf of this tree, we are going to query the green vertices. Or the green cut. So this is what our little tree looks like. And now, since we've arrived at 1 vertex per set, we can basically contradict the original axioms, the mod 2 equations that define the Tseitin constraint. So let's look at one of the leaves of this tree here. So this one here. So on this path to this leaf, we've determined that the sum of the edges crossing the yellow cut is 1, and the sum of the edges crossing the green cut is 4. And this contradicts the constraint here for vertex 5, which says that the mod 2 sum has to be odd. So we can immediately just get the empty polytope from that together with the constraint, the Tseitin constraint. Similarly for this guy here. And for this one here, because we contradict the constraint for the yellow vertex. But now let's look at this vertex here. So this vertex corresponds to Tseitin to stabbing planes lying to us, right? Because it says that the sum of the edges going into green is 3, is odd, and the sum of the edges going into yellow is also odd. But we know this can't be true because we've determined that the sum of the edges crossing the red cut is also odd. And by maintaining this sort of consistency here, we can immediately derive a contradiction from this. So this is just by handshaking. You can look at if there's 3 edges in going to the green vertex here, and just one going into the yellow one, either it's crossing here or it's going across here. But in either case, we have to have an even number of edges crossing this red cut, which contradicts the previous branch up here. Okay, so that's the upper bound. Hopefully that's clear. And now let's analyze how large this is. So each recursive step takes at most n squared branches. And this is just because there's at most n squared edges in the graph. And there's at most log n recursive steps. And this is just because at each time, each time we recurse, we split the number of vertices in half, and we recurse on 1/2. Okay, so this gives us a proof of size n to the order log n, which is quasi-polynomial.
No?
Yeah.
I have a general question. So this linear decision tree model, I guess the whole point here is the integrality issue. The linear decision tree model was, sort of very popular old model as just a computational model. You just get a set of real inputs and you want to know some property about them, like are they all distinct and so on. And people studied, more the depth of the tree rather than the size. So are there any relations or this is?
So I don't think so. I looked at it a long time ago. Like one natural thing to try to do is like to get some sort of interpolation between the two or something like that. But I don't, back when I thought about it, I didn't find any connections between these two.
Okay. Yeah, there are some sort of amazing results, like that you can, in polynomial depth, solve the knapsack problem on this.
Oh.
Yeah.
Oh, interesting. I didn't know about that.
From the 80s of Meyer Hofderheide showing that I'll give you a set of real numbers and you want to know whether a subset of them adds up to something.
Yeah, I see.
The basic NP-complete knapsack problem, there's a decision tree of polynomial depth that would do it for you. It almost looks like P equals NP. So I'll leave it for people to figure out why it doesn't. But
yeah, that's really interesting.
Yeah. Okay, so we can talk about it offline.
Yeah, okay, so the second step is to just convert this proof into cutting planes. And to do this, so I'm going to do it in 2 steps. So the first step is to show that this proof can be converted into a model, which I call linear stabbing planes. It's, well, and then the second step is to show that it's equivalent, that this linear stabbing planes is equivalent to cutting planes. This is probably going to be pretty obvious from the definition. So what is linear stabbing planes? So it's the restriction of stabbing planes such that it can only cut away corners of the polytope. It can't stab through the middle of it. So so it's the restriction of stabbing planes such that each internal node has at least one child labeled with the empty polytope. So what a linear stabbing planes proof looks like is something like this. So each internal node has at least one child labeled with the empty polytope. So the strength of stabbing planes was that we were allowed to branch through the middle of the polytope and recurse on both sides. But linear stabbing planes is restricted to not be able to do this. So now we're only allowed to cut away a corner of this. And linear stabbing planes is equivalent to cutting planes. And this might be obvious to you. Basically, what cutting planes can do is cut away corners of polytopes, cut away sides of them. And this is also exactly what linear stabbing planes can do. So I'm not going to prove this, but it's pretty straightforward. Both directions, you just list all of the inequalities that linear stabbing planes queried, and then you basically show that you can that each of those are valid cuts for cutting planes, and in the other direction, you list all the cutting planes cuts in order, and then you show that each of those are valid linear stabbing planes. Okay, so now we want to convert the stabbing planes upper bound into linear stabbing planes. And kind of try to hand wave this.
No?
Yeah.
Just a question. Looking at this picture of the linear case and the general stabbing plane case, well, a more basic question: what coefficients are you allowing in your initial system? I mean, how big are they in the axiom inequalities? Can they be polynomial size or polynomial number of bits?
So with the axioms, they're only going to be, well, for Tseitin, they're only going to be, I think, Boolean. But for
general,
like each of these queries are going to be, we're allowed any amount of, any integer coefficient. In this paper by Deduce and Tawari, they show that polynomial bit length always suffices.
Yeah, so yeah, it seems, there are some geometry. Yeah, that was one question I had. Yeah, so this is more or less known, at least for Boolean solutions, that polynomial number of bits of size. But just looking at the picture of the stubbing plane and the linear stubbing planes, if you have a stubbing plane proof with which cuts in the middle in the way it shows in the picture, can't you simply ask all parallel shifts of this hyperplane? There'll be, I mean, if the coefficients initially was small in the axioms, there'll be, I don't know, n of them, and just peel away, or some of them will cut many vertices, and that's not allowed.
Yeah, yeah. I think you're going to get a tree with very yeah, I think this would correspond to basically getting a lot of different branches. Like what you have to worry about is the cuts. So maybe you cut like this, and then you cut like this, and then the next time you cut like this, and here, and then here, if that makes sense. But then you have to refute this branch here, as well as this side of the polytope. I don't know if that makes sense to you.
No, that's a problem, but okay, we can.
Yeah.
Okay.
Yeah.
Let's continue on that. Yeah.
So the observation that you need in order to show that linear stabbing planes can simulate this stabbing plane's refutation of Tseitin is that the stabbing plane's refutation isn't actually using like the full power of stabbing planes. Kind of what it's doing is it's moving from the outside of the polytope inward.
Well, that was more or less what I was suggesting, but
yeah, that's what I
said.
Yeah.
So the stabbing planes thing does do this, and we're able to simulate it here, but I don't know a way of doing this in general. So if you look back up at what the stabbing planes proof did, you queried whether the sum is equal to 1, equal to 2, so on and so forth at each branch. And the thing to observe is that basically what it's doing is it's starting at the outside here. When it's querying if it's 0, then that corresponds to this face here of the polytope. Then it's refuting this face. So we look at this subtree here, and it's refuting this face here. And then we move on to the next guy here. This corresponds to when the face is 1. So basically when we've refuted this face when it's 0, we can then derive that it has to be at least 1 using a valid stabbing planes cut. I'll go through this in more detail in a minute, but this is just some intuition. So this is when L is equal to 1, and then you kind of move your way through the polytope, refuting each one of them. So the point is that you're moving from the outside of the polytope inward rather than branching through the middle of the polytope. And this basically allows us to simulate, or allow Deduce and Tawari to simulate the stabbing planes proof.
I don't understand why it's not a general simulation. I mean, that was more or less what I was asking before. If you had anything in the middle, you can just look at all parallel shifts of it and just do them one at a time. I
think the issue is when you're doing it recursively, whether you get blow up or not.
Yeah.
You don't do it recursively. You want to know the answer in the middle. And so you also get answers in all the shifts. You just, it seems like you, instead of 2, the branching factor changes from 2 to n if this diameter or width of the polytope is n. Isn't this what happens in the specific Tseitin thing? That
are you saying that you would end up with a stabbing planes proof or a linear one?
A linear one. I want to convert a stabbing. I mean, that's what I guess Noah is doing for the specific, Tseitin. But I just wonder why it's not a general simulation of stabbing planes by linear stabbing planes. Whenever you are asking any hyperplane which potentially has something to do with the middle, you look at all its shifts and just do them one at a time from the, from outside the polytope inwards and sweeping all through the.
But is it clear when you're at the end of the shift, the beginning of the shift, that when you recursively continue that you're done?
If it's, well, I don't know. I mean, it's, if
I think that's the, like if you
Yeah.
From the picture, it looks the same, but
yeah, maybe we can talk about it offline. One of the conjectures, well, one of the open questions that I'd like answered is whether stabbing planes and cutting planes are equal. So when we were understanding what was going on in this proof, we did think that something similar to what you seem to be saying would allow cutting planes to simulate stabbing planes. But that didn't work out for a bunch of different reasons. But yeah, maybe if I explain this in a bit more detail, it'll be kind of clearer where the problems come in. So the main tool we're going to use here is the following lemma that was proved by Shriver in the 80s. And what it allows us to do is that if we have some polytope and a face for that polytope, and we have like a linear stabbing planes cut on this face, then we can simulate this linear stabbing planes cut on the polytope itself. So let P a polytope. AX greater than or equal to B, valid P. What I mean by valid is I mean that every point in the polytope P satisfies AX greater than or equal to B. So we're going to let P face be, so P face is just a face of this polytope. It's P intersected with AX equal to B. And we're also going to let CX greater than or equal to D plus 1 be a valid linear SP branch P base. Okay, so we're looking at some linear stabbing planes branch from the face of P. Then there exists another linear stabbing planes branch prime plus 1 from the polytope P rather than from the face, such that if we restrict to this face, this cut from P is at least as powerful as the cut from the face. Yeah, so what this is saying is that if we have a linear stabbing planes branch on the on this face, then we can kind of simulate this branch on the polytope itself. And with repeated application of this lemma, you can, if you have a refutation of a face of a polytope, you can sort of simulate that refutation on the polytope itself. Okay, so I'll prove this lemma. This is, it sounds a little eerily like what Avi was saying. Basically what we're gonna do is we're gonna take the inequality cx greater or equal to d plus 1, we're going to shift it so that it no longer depends on this the ax less than or equal to b, the half space of the face that isn't valid for p. So let's look at p face. And maybe this is cx greater or equal to d plus 1. And because it's a linear stabbing planes branch, we know that cx less than or equal to d is the empty polytope. So there has to, by the compactness of the polytope, there has to exist some delta in 0, 1, such that cx greater than or equal to d plus delta is valid for p, or p face. So just meaning that every point in p face satisfies this inequality. So because of this validity, by Farca's lemma, we can write cx greater than or equal to d plus delta can be written as a non-negative linear combination of the facets of p face. Okay. So the idea is that we want to take cx greater than or equal to d plus delta and shift it so that it no longer depends on ax less than or equal to b, which is the inequality that is not valid for p. And if we shift it so that it doesn't depend on this anymore, then then this inequality will be valid for the polytope p itself. And furthermore, if you shift by factors of ax equal to b, then because p face includes this constraint ax equal to b, it doesn't really change anything. So I'll show you that in a minute. So we're going to let kappa be the coefficient of ax less than or equal to b, which is negative ax greater than or equal to negative b. And we're going to define a shift, which is kappa star. Now we want it to be integral. And that's basically because we want to preserve that delta is going to be in 0, 1. So such that kappa star minus kappa is greater than or equal to 0. And now we're going to shift cx greater than or equal to d plus delta so that it only depends on ax greater than or equal to b, not on ax less than or equal to b. So C prime. Okay. So two things to observe. The first is that C prime x greater than or equal to d prime plus delta is valid for p. And this just follows because cx greater than or equal to d plus delta could be written as a non-negative linear combination of the facets of p face. And we removed its weight from ax less than or equal to b. So now it just depends on the facets of p. And so it's valid for p. And the second one is that C prime is integral. Same with D prime. Okay. And so now let's draw P. Maybe this is C prime X greater than the D prime plus delta. So because both of these are integral, this means that this guy here is fractional. In particular, the fractional value is given by delta. And so that means that C prime X greater than or equal to D prime plus 1 is a valid linear stabbing planes cut because C prime X less than or equal to D prime is the empty polytope. And that's just because we knew that this C prime X greater than or equal to D prime plus delta was valid for the polytope, and that delta was in 0, 1. Okay, and so the last thing we have to verify is this property, that this cut that we made from P, this C prime X greater than or equal to D prime plus 1, is at least as powerful when we restrict to the face as Cx greater than or equal to D prime plus 1. Okay, and to see this, let's restrict to this face and add in the constraint plus 1. So this is the same thing as P face, just because this is P face. Minus kappa star X greater than or equal to D prime plus 1 kappa star AX. So I've just subtracted kappa star times AX from both sides, but now because we have AX equal to B, because every point in this polytope, this P face polytope, satisfies AX equal to B, then this just means that AX is equal to B, so we can change this this guy on the right-hand side to B. So we have that this is equal to P face intersect C prime X, or CX greater than or equal to D plus 1. Well, D prime plus 1 minus kappa star B, and then this is just equal to D plus 1. And this is just by the way we have defined C prime and D prime. Okay, so all we did was we took this half space, which was a valid linear stabbing planes cut from P face. We shifted it so it was valid for P, basically. And then we used the fact that AX is equal to B on this face in order to show that these two cuts were equal. Okay, so that's the proof of the lemma. And repeated application of this lemma allows us to simulate any refutation of a face on the polytope itself. So what I mean is that, let's say we have a linear stabbing planes refutation of some face of polytope. And I'll call this pi. Then there exists a linear stabbing planes derivation just by applying this lemma to each of the cuts along here, such that this guy is empty, this guy's empty, this guy's empty. This guy may not be empty, but if we restrict to the face, then it is empty. Does that make sense? So I'm just applying this lemma, this Shriver lemma, repeatedly to all steps in this refutation of p-face. Okay, so now the last thing we need to do is prove this theorem. And the idea is to basically do a bottom-up replacement of the stabbing planes proof using the Shriver lemma. So let's fix this. Yeah, fix. So we're going to fix the aforementioned stabbing planes refutation of Tseitin. And the idea is a bottom-up placement using Shriver. Okay, so maybe this is the stabbing planes refutation. And we're going to maintain the following invariant. At each node, so we're going to do this bottom up at each node U with children U1, U2. We're going to let this correspond to polytopes PU, which is going to be, so maybe this is U here, and PU is just the intersection of all of the queries leading from the root here of the down to the node U. And similarly, we have PU1, PU2. So this is just the stabbing planes refutation from before of Tseitin. And maybe we queried AX greater than or equal to B, AX less than or equal to B minus 1. So in particular, this means that maybe PU1 is the same thing as PU intersected with AX less than or equal to B minus 1. Right? And we're going to maintain that we have refutations of both children of maybe refutations pi U1, pi U2 of U1 and PU1, PU2. So we have refutations of each of these polytopes, and what we're going to do is we're going to build a refutation of PU. So is that clear?
No, I'm not sure if you're aware of it, but it's already noon.
Oh, yeah. Okay.
People want a break or.
Yeah, it'll take a second to finish this and maybe then have a quick break, and then I can mention some stuff on the last topic.
Sounds good.
Okay. Yeah, so our goal is, so we have refutations of the two children, U1, U2, inductively, and we're going to build a refutation of U, and then we're going to do this all the way up until we reach the root, which will then be a refutation of the Tseitin polytope itself. Okay, so what we can do is So let's look at what the stabbing planes branch looked like. Okay, so what we want to do is we want to apply, so we have a refutation of the node U1 or the polytope U1, and we want to apply the Shriver lemma in order to simulate this refutation from the polytope U. In order to be able to do that, we need to show that, so maybe this half space corresponded to L being less than or equal to 3. This one corresponded to L being greater than or equal to 4. So yeah, recall that every node in the, every recursive step in the stabbing planes proof of Tseitin corresponded to one of these branches where we had some cut in the graph, L, and we queried whether that cut was equal to 1, equal to 2, equal to 3. So we want to show that for the current polytope, that L greater than or equal to 3 is valid for PU. And why does this hold? Well, okay, so we're at some node greater than or equal to 3 here. So this is the node U. And because we're querying everything sequentially, this means that previously we had, sorry, maybe this is less than or equal to, okay, change that to 2. Yeah, so this means that sequentially we've queried, if this node is querying whether L is greater than or equal to 3 or less than or equal to 2, this means that previously we had queried whether L was greater than or equal to 2 or less than or equal to 3, or less than or equal to 1, which means that the current polytope must contain the inequality, like must have been built using the inequality L is greater than or equal to 2. So that means the L greater than or equal to, sorry, this should be 2. L greater than or equal to 2 is valid for the polytope. So this means that the other half of this face here is valid. So now we consider the face L equal to 2. Which is the same thing as P L equal to 2, PU, which is the same thing as PU1, right? Now we apply Shriver to the refutation. Pi U1, and we get a refutation, well, we get a derivation, pi U1 star, such that PU intersect with pi U1 star. So I just mean all of the branches that we made in pi U1 star. And we intersect with L is equal to 2 is the empty polytope. So that is, we're simulating the refutation of PU1 on PU. Okay, so then you can note that, so this node here corresponds to branching on whether L is less than or equal to 2 or greater than or equal to 3. So we note that L greater or equal to 3 is a valid linear SP cut from maybe branch from PU intersect with pi u1 star. And why is that? That's just because if this polytope PU intersect with pi u1 star together with L is less than or equal to 2 is empty by this thing here. So we're going to append the branch L greater than or equal to 3 to this proof. So this is our proof so far. We branched on pi u1 star, and then we branched on L greater than or equal to 3. And note that because PU2 is just PU together with the branch L greater than or equal to 3, this is contained in PU2, and which implies that pi u2 is a valid linear SP refutation of PU intersect with pi u1 star intersect with L greater than or equal to 3. Okay, so then our refutation of PU is just pi u1 star pi u L greater than or equal to 3 pi u2. And this refutes PU. Okay, so then we just do this inductively from the leaves up to the root, and this builds a linear stabbing planes refutation of the Tseitin formulas. Okay, so that finishes, sorry? Yeah, so that finishes the cutting planes proof of the Tseitin formulas. So if you want to take a few minutes break, then I'll say a couple words on how we prove the cutting planes.
No, I don't know if do you want to just continue maybe?
Yeah, I was wondering the same thing because people might want to leave early, so.
Oh yeah, sure.
Yeah.
It's up to you. I mean, if you feel up for just keep
Yeah,
going,
I can do
that's
that.
fine. Okay.
Okay. So the second thing I want to mention was, well, I want to say some words on random CNF formulas.
Sorry, may I ask a question?
Yeah, of course.
Yeah, so this upper bound will not work for tree-like.
What do you mean for? Oh yeah, it won't work for tree-like cutting planes. That's a good observation. And so I actually conjecture that tree-like cutting planes does not have short proofs of Tseitin. So in particular, if you look at if you take this linear stabbing planes proof and you convert it into the cutting planes proof just using the equivalence, then what you get out is an extremely long cutting planes proof. So it's going to have like n to the log n depth or something like that. So it's going to be really, really long and narrow. And it seems like this depth is really necessary, and it's very DAG-like in its depth. At each branch, you kind of need, at each recursive step, you need to use the previous branches. So here, like I queried L is greater than equal to 1, L is greater than equal to 2, and for L greater than equal to 2, I needed to use L greater than equal to 1, and so on and so forth. And this really creates a very DAG-like structure.
Yeah, of course, there are lower bounds for resolution over linear equations over integers, and this proof system simulates cutting planes with polynomial magnitude coefficients. So everything at every lower bound there would apply also to cutting planes. So it's worth looking at.
Oh, that's a really good point. Yeah, yeah, I'd forgotten about that. What is the magnitude of cutting plane? I mean, the magnitude of coefficients that you need?
A polynomial, sorry, I think polynomial magnitude, yes. Yeah.
Yeah, that's a really good
Not-
point. Thank you.
Okay.
Okay, so in the last few minutes, I want to say a couple words on the random CNF lower bound. So lower bounds in proof complexity for cutting planes proofs have really one flavor to them. What you do is you take formula and you partition its variables into two sets. So let's say F is our unsatisfiable formula. Partition, so the first thing you do is you partition the variables of F into X, Y, such that the X variables map to accepting inputs to some monotone function, and the Y variables map to rejecting inputs of some function which is hard for monotone computation. So all of these lower bounds work by taking cutting planes proof and showing that from it you can extract a monotone computation and then proving a lower bound on this monotone computation. So this was first done by Pudlock and BPR, Benet, Patassian, Raz, in '97. Benet, Patassian, Raz did it for cutting planes with small coefficients. And they showed that exponential lower bounds for cutting planes bounds on the clique coloring formulas. So these formulas are specially concocted so that they're going to have this above property, so that the X variables, these on this clique side, are going to correspond to K cliques. If you turn them into a monotone function, and the other side are going to correspond to K-1 colorings. The Y variables are going to correspond to K-1 colorings. And the method of a feasible interpolation basically allows you to take any cutting plane's refutation of these formulas and extract from them a monotone circuit which separates K cliques from K-1 colorings.
Maybe you could say that Z is the graph.
Oh, yes, good point. Yes. So G of Z is graph. And this guy here is going to say that G of Z has a K clique. So this is intuitively what this formula is encoding. G of Z has a K-1 color.
Well, it's more specific. It says the left side says that X is a K clique in G of Z, and the right side says that Y is a K-1 coloring of G.
Yeah, exactly. So this formula is specifically constructed so that you can turn the X variables into accepting inputs or into K cliques. And the right side, the color side, you can turn the Y variables into K-1 colorings. And then you can just appeal to, and then you can take a cutting planes proof of this formula and extract from it a monotone circuit, which separates these, which refutes, which separates K cliques from K-1 colors. And then you can just appeal to Razborov's lower bound on clique. And that's how B'nai Patassian Raz and Pudlok obtained the first cutting plane's lower bounds.
It's a bit of an oversimplification, I think, of the.
Yeah. That's definitely true.
Circuit is not your normal monotone circuit. It's a monotone circuit with weird gates, and proving the lower bound there does not. You have to modify Rasborov's proof.
Yeah, exactly. So B'nai Patassian Raz showed that for cutting planes proofs with low coefficients, you can extract a monotone circuit. Pudlok had to do more work by showing that you can take from any cutting plane's refutation with arbitrary coefficients what's known as a monotone real circuit. So you're allowed real valued functions at monotone functions at the gates. And then he had to show that you could actually carry through Rasborov's lower bound on clique in this stronger monotone real circuit model. Okay, but the point I wanted to stress in this is that these formulas are specially concocted so that you have this really nice structure where one half corresponds to cliques and the other half corresponds to colorings. So the other approach for proving lower bounds in on cutting planes proofs is via lifting. So I'm not going to say exactly how this was done, but basically lower bounds on cutting planes proofs follow by lifting with the index gadget. Together with a very clever reduction. So what I want to stress here is that lifting kind of imposes structure, like a structured partition, or I guess a structured partition of the variables into sets X and Y, and adds a lot of structure here so that the X variables will map to accepting inputs, and the Y variables will map to rejecting inputs of some hard monotone function, or some function which is hard for monotone computation. All right, so this makes both of these approaches kind of pose problems for random formulas. So random formulas are not lifted instances. So we cannot use lifting to do it. And we can't impose any any structure like they did for clique and color. So what we have to do is we have to show that from a random instance, we can extract a partition of the variables so that the X variables will map to accepting inputs of some hard function, and the rejecting inputs will map to the Y variables will map to the rejecting inputs of this hard function. And that we can get that this function is hard for monotone computation, and so we can use like monotone circuit lower bounds in order to do this. Okay, so the high-level proof technique, which I won't be able to get into, is that first, we generalize what's known as the method of feasible interpolation. So feasible interpolation originally allowed you to take formulas with the same structure as clique-co-clique and extract from them a monotone, extract from a cutting plane's refutation of them a monotone circuit, computing some associated formula. so this is feasible interpolation for cutting planes. And we generalize this to show that from any cutting planes refutation of any formula, any unsatisfiable CNF formula, we can extract a monotone function. We can show that basically the cutting plane's lower bounds follow from monotone circuit lower bounds on this associated function. So all I want to say is that we generalize interpolation to hold for any unsat CNF. And in fact, we do something a little bit more. We show that an equivalence between monotone circuits and proofs in some stronger proof system than cutting planes. And the second step is we prove lower bounds on monotone circuit size of a formula associated with random. Okay, so those are the two steps, and maybe I can say a couple of words on why especially the second step is non-trivial. So yeah, so I've mentioned above that what we have to do is we have to find a partition of the variables of the random formula such that the x variables correspond to accepting inputs, the y variables correspond to rejecting inputs of some hard function for monotone computation. So one of the problems that we have to overcome in doing this is that if you take a random CNF formula and you partition its variables into two halves, uniformly at random or at random, then you're going to expect to find a bunch of clauses where each, a bunch of clauses which depend almost entirely on the x variables or almost entirely on the y variables. And these are going to be very difficult to deal with because basically they're going to, they're going to be very easy in this monotone model of computation. So for anybody who understands the search problem associated with an unsatisfiable CNF formula, so this is the analog of the Karchmer-Wigderson game for circuits. So Karchmer-Wigderson game shows that you can turn any circuit into a communication problem. The search problem shows that you can turn any proof into, at least in standard proof systems, into a communication problem. In the search problem, these clauses where almost all the x variables or almost all the y variables, these clauses that contain almost entirely x variables or almost entirely y variables are going to become very easy to compute in this search problem, essentially. So we have to get around this problem. And the way we do this is by finding a large set of assignments. Finding a partition of the CNF formula such that almost every clause contains kind of a balanced number of x variables and a balanced number of y variables, and showing that we can also find a large subset of truth assignments which satisfy every unbalanced clause. So every clause which contains too many x variables or too many y variables. So that's very, very sketchy. But yeah, I think that's all I have time for. Are there any questions?
How large are the clauses in this?
Oh yeah, good point. So I should just state the theorem that we proved. So they're log n width. So that's one interesting thing, is that we're not able to prove this for any smaller width than log n. So for k being theta log n, requires mobility. Okay. Yeah. So we're unable to improve this to say constant k, which is what a lot of the other random CNF lower bounds hold for. And this seems to be because of current monotone circuit lower bound techniques. So here we use the symmetric method of approximations. And it seems like if we are going to get lower bounds on random CNF formulas for cutting planes with constant width clauses, then this method, well, we're going to need a new method of proving monotone circuit lower bounds, or at least one that significantly improves upon Rasbarov's method or upon the symmetric method, which was introduced by Jukna.
Okay, thank you very much for the talk. Any questions?